Thank you. So the way I structured this is, since what is virtual brain, a few words of introduction. So the yesterday, the today, and the tomorrow. And the tomorrow shall go into the direction of latest developments and links to Ebrains, and of this, many of you are actually a big part of that. Yeah. So the yesterday goes back 30 years by now, and for those of you who have not heard of the virtual brain, what has happened is in the last 30 years, there were developments that are providing us more details about structural constraints we can put upon brain network models, in particular with the advent of diffusion imaging in the 90s, which has contributed a lot to the field of network sciences that in this form at that time did not exist. There was a little bit of network theory, graph theoretical tools to do this, but in neuroscience, it was just emerging. And then it gave rise to what we know today as Connectome and connectomics. Yeah. In 2010s, there were several ICT efforts dedicated to building multi-scale brains and brain networks. So one of them we were involved in, that's the virtual brain, and Randy is also here, Randy McIntosh. He led the brain network recovery group at that time, 2005, out of which then first Connectome emerged. Second, the virtual brain emerged, which was then an effort from 2010 to 2015. So that's what I will talk about, but also 2012-ish, the Human Brain Project developed, 2013, and accompanies us until today. And today we are in the 20s, where these ICT efforts are leading to applications that start becoming meaningful. In medicine, here I'm highlighting personalized medicine, which I will talk about a little bit in terms of epilepsy surgery. Yeah. So the virtual brain, what is it? It's a neuroinformatics platform that takes advantage of human brain imaging data, constraining our mathematical models. And in the virtual brain, the neuroinformatics platform, we optimized simulators that allow simulation of this type of network models on the full brain network scale. We are extracting information from the MRI. It's individual information, yeah, that allows us to constrain the brain structure, the cortical and subcortical surfaces, and using diffusion imaging, we can extract the connectome. Yeah? We put those pieces of information together, we co-register them, we put them together in the same space. A parcellation is being performed to which the tractography is being aligned, and then allows us to span the cortical and subcortical surfaces that are now parcellated. In the top right corner, you see an image. So each parcel we represent by a network node spanned in three-dimensional space in the head and connected by what we call the connectome. Yeah? So the structural white matter connections that are connecting these individual nodes. The mathematics that is behind there, you see on the top, and it's psi dot. The dot is not really visible. So a differential equation that has a spatial component. The spatial component, if we are dealing with network nodes, it's discretized. Yeah. If we are dealing with continuous space, to which we will come later, it's spatially continuous, and then we are dealing with neural fields. So this n of psi is the intrinsic dynamics, the mean fields that you were probably talking about already, that represent the dynamics in a network node, plus then you see the integral here with the local connectivity. This is what you were probably plotting earlier, the local connection density, excitatory and inhibitory across the cortical surface, if there is a surface. If not, this term disappears, plus, and then you have the global connectome. This is a white matter connectome, and you see the big difference is g of x, x prime. It's not translationally invariant, yeah, as opposed to the first one. and the distribution connection equations we saw in the previous talk. So it's a translationally variant. And the time delays you see in this term, this breaks loads of this symmetry. So because it's a full brain network, you have signal transmission via time delays. And because it's not translationally invariant, you can actually not describe it by a partial differential equation. So you need to stay on this mathematical description. That's a mathematical skeleton thereof. Yeah. And then what we are...
Do I understand well that actually in the first term, you don't take delays into account?
The first term, you mean the end?
The second term.
The second term. You can take delays into account, but there the connection distance is on the scale of millimeters typically, which means the delays are negligible, even though, so they're on the time scale of 1-5 milliseconds, something like this. So typically we ignore these delays there, yes.
But you know that these local connections are slower as well.
I know, they are typically non-myelinated, most of them at least, but still, we are here ignoring them. We could put that in, it would be inconsequential here for what the story that I'm telling, yeah? But compared, if you look at the full brain network scale, these local connections, the time delays there are negligible. Estimates for the long delays are from a few milliseconds until to 100, 150 milliseconds, yeah, depending on the length and the propagation speeds, how you scale them. So they're really negligible to the full brain network scale. Yeah. It depends on the question that you ask. Yeah. Here we are on the full brain network scale. Okay. I will not enter much into this here. We are equipping each network node by the mean field models that are developed, many of those in the lab of Alain. So this Devolo et al., this Zerlo et al. So this type of models we are putting there. Yeah, I'm not entering into this. In this, I wish though to enter, and this is one of the reasons for the importance of the virtual brain platform, because it actually bridges a gap between sensor and source signal. The sources here are on the cortex in this representation and are aligned vertically in this illustration, vertically to the cortical surface. And there each source is roughly on the scale of 1 millimeter, because then at some point the mean field approximations, they break down. But we are computing the link between the sources, yeah, and the sensors, which is MEG, EEG, ECOG, or it can be microelectrodes or stereotactic EEG, as we're using it in epilepsy. So this is part of the neural informatics platform. So in summary, we do the following, yeah. We reconstruct the cortical surface, we parcellate, we replace each parcel by a mean field network node, so a point-like structure, yeah, and then we connect it with a white matter connectome in this representation. And Fred, once again, here in this case, it's point-like network nodes. We're not talking about network about surfaces, which is probably 95% of all the virtual brain applications published at the moment. Yeah, and then the good thing about this is, so it's constrained by individual connectivity. But the good thing is we can now do things such as sticking electrodes at specific locations, specific for a patient, or as I said, from the source to sensor space, you can do MEG, EEG, functional MRI, you can make the jump to the sensor space. And that's actually very, very important if you want to interpret your brain signals. Yeah, there is a platform, Python-based, open source, that allows you to, so you can go in the Python notebook, or you can run it from the interface. You can run individual simulations. You can manipulate the connectivity as you see represented here. Below, you can define different mean fields. So TBB is, TBB as in the virtual brain, is model agnostic. So we have a growing number of mean field models in there. And the latest is being Zerlo and Destex, for instance. Yeah? And then you can perform the simulations either in the source space, either and then project directly also on EG, as you see here, Analysis capabilities of the platform are limited because it's more a simulation platform and data organization platform, as you see here. But you can, it's optimized for batch jobs, so you can run large parameter sweeps. But also one thing that is really cool is very often the question is, where are you in parameter space? So for the each mean field model, which I'm not showing here, you can go in a state space representation, and you can change the parameters, and it changes how the flow changes of the mean field model that you want to operate. So that's actually extremely useful. Yeah, community is very large. I have not looked it up recently, but it's more than 30,000 registered people, downloads. One thing that is important, it's also very easy to use in another species, such as a mouse, such as a rat, or the macaque. Yeah, because if the data are in the appropriate format, you can use it. The mathematics stays the same, the concepts stay the same. And you can also use different connectivities. Here, a representation of probabilistic mouse tractography. There was a lovely study, and that was by Melozzi et al., yeah, a former PhD student in my lab, yeah, who worked with 19 mice, scanned, excellent reconstruction in tractography, deterministic, probabilistic, but we also worked together with the Allen Institute, yeah, and there we had essentially the capacity to compare different types of connectivities, put them in there. We could start mixing them. We could start building surrogates and ask actually very detailed questions. Here conceptually, I do this. Now I don't have a mouse, so follow my words. Go to the top left. There you see multiple mice and individual mouse. This is a first conceptual difference. For the multiple mice, this is coming from the Allen Mouse Atlas, because there it's coming from tracer data. Yeah, so their personalized or individualized information is not the case. However, you have high resolution information there, beautiful data. You can construct from, so along this from the tracer data, you can construct the virtual mouse brain, and you can simulate the source data, project on bold data, simulate it, and can then compute your favorite metrics for evaluation, such as functional connectivity. You can also put the mouse in the scanner and perform fMRI, but also DTI, anatomical MRI, and go through the other two streams, and then you have an individual mouse model. And again, you have the empirical bold data, you have the simulated bold data. And then you can compute your favorite metrics to evaluate what is happening in the different mice models. And then you can start actually looking at what connections are missing when you compare the tracer-based connectome versus the DTI-based connectome. Which method is better, deterministic, probabilistic, in terms of, and this is a perspective, generating the dynamics in terms of brain activations as observed here in this particular case in fMRI. We have done that, and it's a beautiful study. I ask you, please go to the bottom right, and there, in terms of predictive power, yeah, I want to highlight the following. In terms of predictive power, what you see in this violet, what you see there is experimental functional connectivity. So this is scan, rescan of the mouse, compute the functional connectivity. So Pearson cross-correlation activation between individual areas, and then scan, rescan this, you get up to between 55 and 60% reproducibility. So there you take the mouse, its own brain, its own model. So this gives you a benchmark. That's the best you can do, the best you can expect from this type of metric. When you do this with a tracer-based mouse, you can get actually close, almost 50%. Yeah, and this is compared to the individual functional brain dynamics of the individual mouse. The next best is deterministic MRI, coming from the individual connectome, so the individualized mouse brain. And you see the tracer-based is better. You see also that deterministic is generally better than the probabilistic. This is not too surprising. We're dealing with large-scale brain dynamics, but you also see individual is significantly better than averaged or surrogate or any other brain. From another mouse. I'm not showing this here, but that was the case. which means what we learned from this story is detail matters. It does override individual variability, at least from the perspective of this metrics. However, individual is better than another replacement with the same degree of granularity. This is important because I want where I'm going to guide you in Ebrains is, on the one hand side, detail matters. On the other hand, individual matters also. But we cannot put these two things easily together, detail and individual. We need novel concepts in order to do this. Yeah? That's one of the key messages come from here. Today, where are we today? So coming out of my mouth, in this case, I'm talking about epilepsy. I do this often, and I just want to position this. How far can we go with this current state of the art of technology? Yeah. So epilepsy for the human, in epilepsy, we want to build individual virtual brains, helping us to understand epilepsy better. Yeah. And in particular, here we are making, taking advantage of this huge epilepsy unit that we have in Marseille, where stereotactic electroencephalography is one of the leading technologies, which you see represented here to the right. We insert electrodes, so-called Talarak electrodes. They're about, when you look at me, that long, and they have a spacing of the individual contacts, either 10, 15, or 20 contact points, spaced 2 to 3 millimeters each, allows us to go into the volume and obtain gold standard data directly from the human. The idea is to estimate the epileptogenic zone, so their network, which is capable of generating self-sustained oscillations, and then propagate through the network and essentially incapacitating the patient because of this seizure propagation. Yeah? This is the best technique we have at the moment to estimate the EZ, the epileptogenic zone. But if you look at this graph on the bottom left, what you see there is actually, if you average across all epilepsies at the moment, we have a success rate of about 50 to 60%, better for temporal lobe epilepsy, but in principle, success rate, the message is the following: success rate has not improved over the last 30 to 50 years. My graph shows roughly 30 years, but estimates go 40, 50 years, something like that. Yeah, which means we want to do better. And that's the way how we are approaching it. Here you see the workflow that we are using. On the left-hand side, we put information together. We put mean fields in there. We build the virtual brain connectomics-based structure, and then we apply methods of Bayesian inference machine learning in order to estimate the parameters for the brain. And these parameters in particular are also epileptogenicity and epileptogenic zone. I'm not entering into this here at all. I'm just pointing this out. This is a large and exciting field because there are very deep questions in terms of neurodegeneracy, in terms of identifiability, in terms of convergence, diagnostics, etc., that are occupying much of our time. Yeah. Once this is done, then you have an autonomous in silico platform. These are simulated data here. Yeah. Autonomous, which means the blue dots, they represent individual sources, and autonomous means you can run it now, simulate it, and run seizures based on the parameters that you estimated. And then the red balls, when they become bigger, they indicate the energy that is in this particular system. And in the electrodes is in white little spheres is what you actually measure. And these are the time series that we have plotted here. We can do this now actually on both levels. Yeah. Again, data, this time measured on the electrodes. So these are the electrodes as EEG electrodes that are represented here. Now you can do the same actually on the source space and actually estimate the corresponding source activity that is capable of generating the type of activation patterns that you observe there. And we can run this 1,000 times, 1,000,000 times, and actually scan, perform interventions, resections, or even stimulate in order to test hypothesis. Yeah, this is what we do. Clinical trial since 2019 with 400 prospective patients. And we are estimating these parameters that I just showed you. And here you have a representation before surgery. Here that's temporal lobe, temporal pole, epileptogenicity heightened before surgery. And then you go down and you see after surgery. This is what is being resected, yeah, this resected tissue. We're doing this. And we're doing this in France in 13 centers where the workflow is as follows. We collect patients in these 30 centers where the data are harmonized, centralized in Lyon, and then being anonymized, of course, sent to Marseille, virtualized, analyzed, information is being compressed, and an estimation is being sent back to the clinicians where they use it in their clinical staff meetings for patient evaluation. With the intent to figure out there is a blind group, so there is a positive group and so VP positive, VP negative group in order to have a comparison. The target is we want to figure out if this type of virtualization technique changes actually the decision-making of the clinicians. What you see here is our development at the moment. So we are at 128 patients as of yesterday, of which 75 have been randomized. I want to point out March through May 2020. This is a COVID when all the centers were closed, but then it really finally took off. So this is where we are. So we got slowed down actually a lot. We should have been at 250 by now, but it will take longer. First results are promising. Actually, we are not doing, or VP is not, it's influencing the decision making. It's not doing necessarily better than the clinical hypothesis, but we cannot tell this yet because after the surgery, we have to wait for 1 year to see if the patient is actually seizure free. This is being measured by the Engel score, Engel class 1, 2, 3, and 4. Engel 1 is seizure free, Engel 2 is situation largely improved, hardly any seizures, and 3 and 4 is less good and less desirable. Yeah. So, and what I'm plotting here is precision and recall. So these are binary classification metrics, very similar to specificity, for instance. Yeah. So, and there it's essentially, it goes down when there is discrepancy with what we have with the surgery that has been actually executed. Yeah, the seizure success goes down. And this is one very simplistic marker that we use for guidance at this very early stage. So this is promising, all I want to say about that. So more importantly, so yesterday, today, where are we going? And I already indicated this where we want to go. High resolution is one, personalization is the other one. Multi-species is also a direction that we want to take, and which is important for the story here. So in order to be able to go to a high resolution, we need the relevant ICT powers. And this is what is being provided by Ebrains. And Ebrains is, I assume you have not talked about Ebrains yet. Ebrains is one of the deliverables that is coming out of the Human Brain Project that has now lasted almost 10 years. Ebrains is and will already exist to some degree, but very bumpy, reality check, very bumpy, but is supposed to work very smoothly and wonderfully in 2023. European infrastructure, ICT, neuroinformatics infrastructure dedicated to neuroscience research and clinical and technical translation. This is a vision. Yeah, and federated means the following. When you think of European infrastructure, probably what may come to your mind is CERN in Geneva for experimental high energy physics, these accelerators. Here, federated means is there is no real physical geographic location other than Europe, yeah, but it's distributed across different places, countries, cities, yeah, and it defines a federated virtual space in which neuroinformatics processes can be launched. And these processes are being supported by a very basic infrastructure that is composed of different types of tools, yeah. In particular, hardware. There are multiple supercomputers and high-performance computing centers that are behind that. Phoenix in terms of data storage of large data sets. But there are also tools for data curation, tools for atlasing, data that are being stored and saved for multiple different species and are being curated in the same brain reference space as the brain models that go across multiple scales, from the subcellular to the cellular, to the microcircuit, all the way to the brain, full brain scale, what we're talking about. For more details, please check it out on the website, which is on the bottom right. There are also, beyond hardware, there's also software for simulation. There are multiple simulation engines that are being supported and that are actually interoperable. I will show you an example with regard to this. That's highly non-trivial if you want to have a mean field, as we have been talking about, speak to very detailed, morphologically detailed neurons. You need processes and timing constraints to put this in place. One big contribution of Ebrains is the following, and here let me guide you through this particular workflow here. First of all, there is loads of information about the brain across multiple scales, across multiple decades, across multiple labs, and across multiple types of information. Yeah? To put all this data together requires a huge, enormous effort in terms of data curation. We are talking about cytoarchitecture. We are talking about structural information, as the way we have just talked about. We are talking about, for individual areas, neurotransmitter, receptor densities, yeah, and this across cortical and subcortical areas for different species. This requires huge high-performance computing powers that are dedicated to this in terms of storage also. All this information is being organized, the data is being curated, and in order to make it accessible, findable, treatable, yeah, you need services. You need data services, a so-called knowledge graph that allows to organize this type of knowledge and make being able to render and process this information. Then it needs to be mapped into an atlas spanned in a three-dimensional space in which these data are organized and made accessible, interpretable, yeah, and communicable. Yeah, and across all scales. This is another service that is being offered. And then we want to not only to visualize this and look at it, but we want to use it. So it needs to be mapped into within the same brain reference space upon a mathematical structure. And this across scales. This is the work of many years in the sub-project 4, in the Human Brain Project in theoretical neuroscience, where the individual scales are being connected in order to translate the information on the neurotransmitter receptor distributions from one scale to the other, such that it can inform mean fields, for instance. Yeah? So there are mathematical, computational, informatics requirements that need to be made all interoperable. This is one, or in my opinion, the major key contribution of Ebrains to make this flow possible. In the context of we have just discussed, yeah, you see in the left branch, this is what I described to you in terms of the virtual brain as it exists today. When you look at the right branch, yeah, this is what I discussed with you here now in the context of tomorrow, the connectivity. And this, I cannot point with a mouse, but when you see this thing that points towards a brain region and then goes across different scales, this is supposed to be my best illustration or cartoon of the multi-scale translation of the information, the data we have in there, and informing the mean fields in an individual brain region, and then going through the workflow that we just machine learning, etc., in order to obtain a better estimation of the epileptogenic zone, for instance, in the case of epilepsy.
Viktor,
I remind you.
It's try to press C. I think I found out. Just C.
Just C.
Yeah.
Can you
We
see?
have the mouse. Yeah, it works.
Yay, perfect. You
See
are
it. Yes,
useful.
great. Yeah.
You are very, very useful, man. Thank you. Wonderful. Thank you. Yeah.
This is why we need experimentalists in the
yeah,
group.
but Fredo, next time a little faster, please. Yeah.
I clicked on there to stop you before. I mean, it was so.
Okay. So now I'm making reference to this mouse story I told you earlier. Details can enter in here in the human brain. Yeah. And this is essentially lots of the work that I'm citing here. So the detail can enter through this particular part here. Yeah. That you already discussed. Yeah. And needs to inform this. And I remind you, detailed models perform better on the full brain network level than they outperform individual variability. Yeah. But where are we in reality? A little reality check. Yeah. 100 to 200 network nodes, 95% of all the papers, they're dealing with that. Yeah, looks like this, about 100 nodes on the left, 100 nodes on the right. Where's the mouse? See? Yeah, here we go. Can you see it?
Yeah, press C again.
I'm pressing C. Can you see it now?
Yeah, yeah.
We can see it, but you should not move it too fast.
Okay. So state of the art. If you're on this level of resolution and you collapse the tissue, then we are dealing with region sizes of 10 to 20 square centimeters, fiber lengths of 3 to 5 centimeters, minimal. Yeah. So it's actually huge. Yeah. There is first information that you should realize. If you want to have high resolution multi-scale information and it's collapsed into these little red spheres that you see here, most of this information is probably completely washed away. Yeah. And there is nothing about high resolution in there whatsoever. This is a big challenge, yeah, because this poses a huge challenge on integrating high resolution data in which thousands of laboratories have invested lots of efforts for decades to collect them in very, very high resolutions. Yeah? So it's a waste. Yeah. Number two, source to sensor mapping is suboptimal. In other words, it really sucks because when you want to have electric mapping from the source to the center, it's not just the distance that matters. Yeah. But it's actually the dipole momentum. How do you compute the dipole momentum, average dipole momentum for such a sphere when it is actually coming from a folded cortical surface with 20 square centimeters? Yeah. We need better concepts and better solutions. Yeah. And then, of course, I suspect you were talking about propagating waves. The notion of propagating waves, traveling waves in a representation like this is limited. Yeah. So we need to do better. Yeah. And one approach would be that we have to make the transition from discrete to continuous models. Or mathematically speaking, we need to go from neural state vectors to neural fields, yeah, to spatially continuous models. Yeah. And we can do that. Yeah. But we need resources for this, and this is Ebrains. Yeah. Network size, what we can run on our computers at home, in-house, 20,000 nodes. I can do this. We can do this. Yeah. It takes a long time on our high performance cluster, but it is doable. What is coming out of FreeSurfer as a standard resolution when you want to have this meshed here is 260,000 nodes. No way we can do this. With 260,000 nodes, we need different computational resources. And then we are on the scale of roughly millimeter resolution. And this is wonderful, yeah, because with millimeter resolution, we can add in all the details that we want to have in the system. Yeah. And going below this, there all the statistical physics of mean field theories becomes actually very questionable. Yeah. So this is good. What I'm showing here in this part is actually now our proposal, conceptual proposal, how to merge the high resolution world with the individual world. And this is hierarchical Bayesian inference. Bayesian inference we are already using to estimate and personalize the network models for the discrete node-based models. Yeah. And what we can do is we can build a higher resolution model, yeah, from non-individual data, and then introduce in the Bayesian inference framework priors coming from the individual, from the brain imaging, and use it as a priors, so-called informative priors, yeah. And this provides the best of the two worlds, combining individual and high resolution information. And here, just for the example, what you see here is structural connectome, individual structural connectome, a range of Bayesian inference metrics. This is leave one out, from a different individual mouse, from several other, from you see when you do this for many different individuals, it doesn't get better, or some type of surrogates. Individual information is always the best with an informative prior. So what you can do now in this high resolution mesh, you can put these dipole momenta on top, and suddenly, and in order you can actually compute and take advantage of the alignment, perpendicular alignment of the pyramidal cells perpendicular to the surface. So you suddenly have the directional information. Yeah. And you can actually now do things such as you go along the neocortical mantle, yeah, and then you continue into the rhinal cortex and into the hippocampus. So you can actually start talking about real propagation along the continuous tissue, yeah, and build very detailed models, yeah. And you can, because you have this high resolution, you can actually use now the high resolution data we have available from different colleagues, such as Cyril Poupon, yeah, Jean-François Mangin, etc., and use the detailed information from the cortex and the detailed information from the big brain in Jülich, for instance, from the post-mortem brains that are reconstructing cellular density, the cytoarchitectural skeleton, etc. And we can make this region specific. So like this, we get the best of the two worlds. Here you see the U fibers, introducing them into the model. And then we can run this type of simulations. Here you see a seizure that will emerge at the temporal lobe. Yes, it does, at the temporal pole, and then propagates across the cortical surface. Usually this would have been two nodes, but we can start talking about propagation patterns. Yeah, and and here we can reconstruct the hippocampus, for instance, in much detail. You see a classic stereotactic a needle with the different contacts, and you see the distribution thereof. So this has promise that these high resolution epileptic brains will do simply a much better job, because in our experience in the clinical trial, this contamination that comes from the source to the sensor projection is one of the biggest contaminating factors in the personalization of the brain. Yeah, and here you see this particular example. For instance, if you do it just with distance mapping, the source to sensor mapping, this is what you get. Yeah. And in reality, you should get this when you perform the model inversion, because you have the different directions and the foldings of the cortical surface. So it's an approximation, but it's far off reality. Yeah. And the other key thing, and that's the last message I want to get across, is the following. In Ebrains, we can also perform co-simulation, so using regions of interest with different resolution. Yeah, and here this is an example. This is now a mouse. We are doing it currently for the human, and the first human hippocampus we hope we will have ready by the end of this year. That's Michele Migliore's work. He has done that already for the mouse, is reconstructing it using either the nest or the blue brain simulator, so the neuron simulator, but for the human, he's going to do it with a nest simulator and integrate it in the virtual brain. Then we have region of interest for the hippocampus. It's very important for epilepsy. So often the hippocampal regions are implicated. Yeah, and we co-simulate this simultaneously with the TVB, and then we can change the parameters. And for instance, do things such as this: render the hippocampus epileptogenic and get propagating waves in this particular regime, and do this systematically. Yeah. So I'm going to stop here. And that was the tour de force. I thought that may be useful. What is a virtual brain? Where are we? What can we do? How can we carry it into real applications? And then where's the future? Where do we hope to go? In particular, from the perspective of traveling waves along the cortex, what are the challenges that we need to face in anticipation that probably you were talking about traveling waves on the macaque cortical surface. Yeah, I stop here. Thank you very much. And these are my friends and colleagues that contribute to this. Yeah, thank you.